Hey guys, so today we're going to be continuing with our previous topic. We're looking at different trends in the periodic table. So I have kept this periodic table here for reference. Today we are going to be looking at a property called atomic radius. Okay, so radius is a word that we have heard before, right? So radius for us in mathematics, we say it's the distance between the center of a circle to its any point on the circumference, right? That is radius for us. So if I have a circle like this, okay, that's not a proper circle. So I have a circle from the center all the way till the edge. This distance is what we call as radius. So when we talk about atomic radius, we're trying to say pretty much the same thing. Okay, we are looking for the distance between the center of the nucleus till the edge of the atom, till the last most shell or the ultimate shell. Okay, so for example, if you have an atom like sodium that looks like this, we're looking for the distance between the center of the nucleus till the edge of the this thing, or till the electron, more specifically, that's on the edge of the atom, right? So that will be atomic radius for us. But how do we measure something like this? I mean, atoms are so small. How do we find out what exactly it is? Okay, there's one issue with this specifically. If you remember, Heisenberg's uncertainty principle says that you can't really know exactly where an electron is at any given time, right? Because they move so fast. So because of that, we can't really measure it like this. But what we can do is we can take the distance between the nucleus of two neighboring atoms and half it. Okay, so for example, let me take a different compound like iron. Okay, I'll assume that iron has like two big new atoms like this. Okay, so from the center of one iron atom to the next iron atom, okay, that would essentially be two iron atoms, right? There'll be the radius of two atoms. So if I find out this distance and I half it, then I can call them as atomic radius, right? Because half is from here to here, which is one radius, and from here to here, which is one radius. Since they are the same atom, they'll have the same radius, so I can neatly just cut it in half. Okay, so we generally also call this metallic radius if we find it out like this. Okay. For atoms like non-metals, okay, this works for metals only because their atoms are generally independent. But if we look at something like chlorine, which is a non-metal, we look at a chlorine-chlorine compound. Okay, so chlorine forms a compound with another chlorine called Cl2. Okay, chlorine gas is basically Cl2 gas. We take pretty much the same approach here also. Between chlorine to chlorine, the centers of these two atoms, we look for the radius, the distance, and then we half it. That will be the radius for chlorine atom. Okay. Now, since it's very small, we can't really measure it in meters or centimeters or millimeters like that. Okay. We have a specific unit called picometers. Okay. PM, picometer. Okay. So one picometer is 10 to the power minus 12 meters. Okay, so that's basically 12 zeros before 10, before the decimal point of 1. Okay, so 0.00000 all the way 12 values and then 1. Okay, that is one picometer. So really tiny, you need to know. Okay, so if this is the atomic radius, how does it differ from atom to atom? Obviously, every atom will have a different radius. Some are big, some are small, and each atom has its own unique shape and size. So how does this change for periods and, I mean, across the period and down the group? Okay, so first let's talk about down a group. Let's take a look at one of the groups over here. Okay, so one of the groups that we have over here, let's talk about hydrogen, lithium, sodium, potassium. Okay, this first group, alkaline metals group. So I know that hydrogen has just one atom, that one electron, and that would look something like this, right? I know lithium has two shells and three electrons, kind of like this. I know sodium has three shells, 1, 2, 3, and the third one is in the third shell. As you have seen, when you go down a group, you're adding one shell extra to the atom that's above it. So hydrogen has just one shell that we call as K shell. This one has K and L. This is K, L, M. Okay, it's quite obvious since you're adding the shells where the electrons stay, the size is increasing, right? Because the distance obviously increases from the nucleus all the way till the outermost shell. This is 1, that is 2, and this is for 3. It's quite clear that the third shell is the farthest, right? So this way we know that as we go down a group, the size of the atom will keep on increasing. Okay, so yeah, so when we go down a group, we can say atomic radius increases down a group. Okay, below sodium, potassium is bigger, rubidium bigger, cesium is the biggest atom that you'll find in that whole series. Let's move ahead to across period from left to right. Okay, so let's look at a few elements here again. So let's take again lithium, example of lithium. So lithium has two shells, like we know over here. We have lithium, kind of like this, right? Two shells, one electron in the outermost. After lithium, we have beryllium with again two shells but two electrons. Boron, again two shells, but the last shell has three electrons. Okay, so we can notice that while we're going from left to right, the number of shells does not increase. When we're going down, it does, but all of them are using the same L shell as the outermost shell to add electrons. Okay, so you would assume that, okay, since they are not increasing in shells, the radius should not increase, right? Because that will obviously be the last shell, L. But actually there will be a change. Okay, so let's talk about the last element over here. So after lithium all the way, we find fluorine over here. Okay, fluorine, which would be 1, 2, 3, 4, 5, 6, 7. And after fluorine, you'll have neon, which is just one more extra electron from fluorine. Now, which one is bigger, which one is smaller is basically up to where it is. Okay, when you're looking from left to right, we say the atomic radius decreases. Okay, meaning lithium is the biggest atom in this second period. Beryllium is little smaller, boron is much smaller, all the way till fluorine, which becomes like the one of the smallest, and then neon. Okay, now why is this happening, right? Why is the size reducing even though no new shells are coming? Okay, the logic is very simple. We see that there are electrons increasing in the outermost shells, right? But one thing that we are not showing in the diagram is, if you remember, protons and electrons are always equal, right? So lithium, I know, has 3 protons, 3 electrons. Beryllium has 4 protons, 4 electrons. Boron, 5 protons, 5 electrons. All the way, if I talk about fluorine, I'll have 9 protons, 9 electrons. Okay, and all these protons are inside the nucleus. 10 protons, 10 electrons. Now, why this makes a difference is, you know that opposite charges attract, right? The protons and electrons will attract each other. So right now we have 3 protons attracting 3 electrons. So we can say that there is some form of attraction between the protons and the electrons. This is what we call as nuclear charge. So what exactly is this nuclear charge, right? Since there are positive and negative, it is going to be attractive, and mostly it is the electrons that get attracted towards the nucleus, because electrons can move, but protons cannot move out of the nucleus, right? So because of this attractive force, the electron size kind of, becomes smaller because of that, simply because of the nuclear force of attraction. So as we go towards the right, we see that electrons are increasing, but protons are also increasing. So effectively, there's more positive charge and more negative charge at the same time. So because of that, since the charges are higher, the attraction also is going to be much higher. So which is why by the time you reach fluorine or neon, you'll have 9 protons, mean 9 positive charges and 9 negative charges, all of each just kind of attracting each other, right? So fluorine will have the smallest size simply because its nuclear charge is higher than what was before it. Okay, so we know that atomic radius is going to decrease when you go from left to right in a period. All right. So now one question that can arise is, what about ions? Okay, because we know what ions are, right? We have cations, anions, positively charged, negatively charged. Okay, we know that ions are created whenever an atom will lose or gain an electron. Do ions also change their atomic radius? Short answer is yes, they do. How they change again depends on the type of ion that we are looking at. Okay, so for this, what I'm going to talk about is both the ions. We'll start with the positive ion, then we'll go to the negative ion. Okay, so an example of a positive ion is sodium. Okay, so sodium for us is Na plus. You know, Na will lose an electron and become Na plus. So normally sodium is first shell, second shell, and then third shell, and that one extra electron there, that becomes sodium with just 2 shells. The third shell, third electron will get knocked out. So this one has a positive charge because when sodium has 11 protons and 11 electrons, that has changed to 11 protons but only 10 electrons. Okay, so if you see, the positive charges are much more than the negative charges over here. Okay, positive charges are more than the negative charge, because when electron goes, the proton does not go. So I can say that because the positive charges are more, they can attract the negative charges stronger. Okay, it's just like having one side with a stronger force, the other side with a weaker force. It will definitely be able to pull tighter correctly. So instead of even, equal numbers, we have unequal numbers. Because of this, what happens is the atomic radius will reduce. Okay. So any positively charged ion or a cation is smaller than its original atom. Okay. Cations are smaller than the original atom is the exact opposite for anions. Okay, if anion is created whenever something gains an electron, right? As opposed to sodium, we have something called chlorine, right? Chlorine for us is an example of something that can become an anion. So I'll take the same method with chlorine. If you can do it on your own, that will be excellent. Chlorine is similar to sodium almost in the fact that it has 3 shells, but 7 electrons on the outside. Now this chlorine is going to gain 1 extra electron, and now it will have 8 electrons on the outside shell. Okay, 3 shells, 5, 6, 7, 8. Okay, so chlorine goes from having 17 protons and 17 electrons to having 17 protons and 18 electrons. Okay, this time the number of electrons are more, the negative charge is higher. The positive is less, so they cannot pull the electric negative charges as effectively. Okay, so because of this, it kind of becomes a little bigger. So atomic radius will increase. Atomic radius increases for anion. Okay, negative charged ions are called anion. Okay, so this is how it is when when ions are concerned. Cations are smaller than the atom and anions are larger than the atom. Okay, so that's it for today. We have talked about atomic radius, which is one of the variants. Tomorrow we'll look at another topic. Thank you. If you have any questions, please drop them in the comment box below.